So, the this lecture video is a first short video exploring the Heisenberg Uncertainty Principle, and it's meant to sort of motivate something interesting. So we want to start from something simple and sort of see the uncertainty principle. So, the simple thing that I want to start with is the example of a rightward moving free particle. So a free particle means no forces. That is, there's no reason for our particle to undergo any accelerations. The reason that this is interesting in particular for quantum mechanics and thinking about the Heisenberg Uncertainty Principle is in this particular example, I want to consider a particle that is not confined, right? That's not kept anywhere. And the way that you would keep a particle somewhere is by holding on to it, right? Holding on to it inside of some locality. So if I want to study a particle that is truly free, then that means I want to study a particle where there are no forces. All right, so there's no accelerations. So if there's no accelerations, then we expect our free particle to have a momentum. We'll say that it's rightward, so we'll say the momentum is positive, and the momentum is constant, is what I'm trying to say. So the momentum is constant. That makes sense if there are no forces on our particle, right? Okay, so just from studying traveling waves, you know that you get a rightward moving particle if you consider things like cosine kx minus omega t and sine kx minus omega t. So rightward actually is shown to us if we just pay attention to the relative sign. So we know that it's rightward simply because of the minus sign. If I wanted a particle going left, I would just make the two terms in the argument of the cosine and the sine, I would make the two terms have a relative plus sign. That is, they just have the same sign, right? But this is necessarily rightward. And so let's study a rightward moving free particle. So the most general, so remember, we want to study, though, in the context of quantum mechanics. So we're going to consider, here's an example, wave function representing a free rightward moving particle. I'm going to write it this way. So there is some normalization constant, and then it multiplies just a simple combination of sine and cosine waves. So this wave function actually has a real part and an imaginary part. But it's not as clear as just saying the cosine is the real and the sine is the imaginary. It's a little more complicated than that, because the truth is A itself could be complex, right? But anyways, it's manifestly, right, explicitly complex valued, psi is. All right, so this is the case in quantum mechanics. So before I do much more with the quantum mechanics, I want to ground us in what is K, in particular, just what is K, right? So K is written up in here. It's multiplying the X. So dimensionally, K is going to be 1 over a distance, right? Because the argument of cosine and the argument of sine and the argument of these trigonometric functions, what needs to be on the inside of the argument actually has to be an angle. So often what people do is they define something called the phase angle. The phase angle is itself a function of space and time. And in this particular case, this angle is this kx minus omega t. So this is referred to as the phase angle for the wave. And our wave exists in space and time. And so this wave in general can travel, is the idea. So K is actually related to the wavelength of this wave, right? This is a wave because, cosine and sine are wavy looking. But what the K does is it tells me about the spatial periodicity because it's multiplying the space thing. Omega tells me about the temporal periodicity. It tells me about the waviness in time. But I want to study K. So K is this kind of a quantity. This is the spatial periodicity. The 2 pi is 2 pi radians because the arguments of cosine and sine have to be angles. They are angles. So here's the angle aspect, right? So it's 2 pi over lambda is what K is. This is called the wave number. All right. But de Broglie, so de Broglie showed us that if you have an object with momentum, then it also has a wavelength, right? So this is the wavelength, de Broglie wavelength, de Broglie wavelength. So let's put this de Broglie wavelength in and understand our wave number as actually related to the momentum. So if I solve for de Broglie wavelength, so lambda is h over p, like this, then that means that K is 2 pi over lambda, 2 pi over this thing right here, h over p. So that means, so if you work with this a little bit, you get 2 pi p over h. So the wave number, is proportional to the momentum. If you further, so actually it's a little bit telling actually to solve for p at this point. So p, if I solve for p right here, multiply the h over, divide by the 2 pi. And this particular combination of h and 2 pi is referred to as h bar. So this is the sort of an updated Planck's constant that includes the fact that we're talking about angles sometimes. So, so h bar k, actually let me erase that and rewrite it. So h bar k. So p is h bar k is a way to bring in de Broglie and talk about mathematical traveling waves, right? So we've got a lot of stuff going on, but we're beginning to kind of like mix up traveling wave with momentum, right? It's a traveling particle represented by a wave where that particle has a momentum. Okay, so so just very quickly, although I'm not going to discuss it much in this lecture, the kinetic energy is related to the momentum this way. If you know the mass, then just p squared over 2m is going to give you the kinetic energy. So, for example, if you know the wave number, right, then you can just plug in, it's h bar squared k squared over 2m, right? So actually, let me rewrite it so it's clearer. Yeah, so anyways, so okay, let's go back and recognize, though, what I want to study. I want to think about Heisenberg's uncertainty principle, right? That's what I want us to think about. So if I want to think about Heisenberg uncertainty principle, I want to think about delta x, delta p being bigger than or equal to h bar over 2, right? So this is the statement of Heisenberg's uncertainty principle. And I just want to think about this free rightward moving particle in terms of what this is indicating. So delta p is the uncertainty in momentum. Delta x is the uncertainty in the location of the particle. And the idea, so I'll just leave it at that for now. But let's think about, so for my free rightward moving particle, I wonder what delta p is. Well, up here, I am representing this particle with a definite value of k. That is, I am imagining putting in a particular value of k, which means a particular value of the de Broglie wavelength. And if I have a specific value of de Broglie wavelength, I have a specific value of the momentum in mind. So if I go down and I describe what my uncertainty is associated with this particular wave function, I'm going to say that actually I have no uncertainty in what I think the momentum is. The momentum is, it's just, right, let's see, let's say the momentum is right here. If I want to know the momentum, I just look at my wave function, take out the value k, which is just sitting right here in that place multiplying the x, and I just multiply by h bar. Okay? So this is true. So what does this mean about Heisenberg uncertainty, though? This means that if delta p is 0, then in order to fulfill this law of nature, right, this fundamental statement about knowledge of these two types of quantities, then if I know momentum to know uncertainty, then I must have 100% uncertainty in my knowledge of delta x. That's the only solution I can have to this, right? And this is an absurdity. It says that you actually have no knowledge about where the particle is. So why is that something that I should actually expect? I should expect that I do not have knowledge about the location because I have no forces holding the particle anywhere, right? This is why it makes sense, and actually I should quit using equals because that's very mathematically bad, right? You just say that free means no localization. No forces could indicate no localization, right? So I have no idea where the particle is, but according to this wave function, I have 100% confidence in what the momentum is. You can kind of see this a little bit further the following way. If you were to draw psi of x at any particular time t, so let's draw the wave function when let's just choose t equals to 0 as a remarkable moment in time to draw our picture. So I'm going to imagine drawing psi for when t equals to 0. So the thing is, though, is my wave function is actually complex. So it's sort of tough to draw a complex function. So instead, what I'm going to do is imagine drawing the real part and then drawing the imaginary part separately. So the real part is, let's say that we normalized this and normalized it so that a was a real number. Then the real part is the cosine aspect, and the cosine aspect just looks like this, right, for all x's out to infinity. And the cosine, you notice, never is different. It just goes like that forever. And for negative x, similarly, all the way out to negative infinity, no change, right? So in a sense, psi of x is interesting for psi of x is interesting for all x sort of equivalently. You know, if you explore x values out here, it looks like this. And if you explore x values down in here, it looks like this. And if you explore x values down in here, it still looks like that. That is, it just looks the same absolutely everywhere from x goes down to negative infinity all the way up to positive infinity. It has no interesting features through space. The imaginary part is similar, right? If you study the imaginary part of psi, it's a sine wave instead. Right? And it's a sine wave of a constant seeming wavelength. Everywhere you look, it looks like the same wave, right? There is no origin. It seems like there's no particular value of x that's interesting, right? All the way out to positive infinity, all the way down to negative infinity. So the wave function is sort of featureless in a sense. I mean, it does have a feature. It has a wavelength, right? But besides that well-defined wavelength, which represents a well-defined momentum, right? Besides that well-defined momentum, there is no well-defined special place x, right? And you can see this actually even further if you remember how to calculate probability. The probability of finding the particle between one place and another place, the way you do this is you integrate from one place to the other, psi star psi, right? This is how you do this probability. So let's study this thing right here. Let's call this thing P of x and t. This is the probability density, right? Psi star psi is the probability density. It depends on space in general, and it depends on time in general. But we have this special wave function where what I've done is I've put in the phase angle, right? It's just sits here and it sits there. There's this relative I, and if I look at what this function looks like, something really interesting happens, right? So it's psi star times psi. It's equal to a squared, right? Because a is going to multiply a, but it's actually a star from the first factor, and then times a. So that's just the magnitude of the complex number a, and you square it. And then the psi star is just cosine phi minus I sine phi. And then I multiply by the rest of psi, cosine phi plus I sine phi. The reason why this is interesting is if I look at this probability density as a function of space and time, it's just equal to a squared, and then it'll be cosine squared phi plus sine squared phi. But the phase angle is common in these two terms, the cosine squared and the sine squared. So this is a squared times 1, right? That's the identity, unit circle Pythagorean identity, if you want. So, so the probability density is actually just constant, right? It's featureless. That is the probability to discover the particle anywhere does not vary in space or time, right? So this is the sense in which the uncertainty in the location is infinity. It's because the probability density has no features. What would a moving localized particle look like? Well, for one thing, if I want it to be localized, then I'd have to have something that maybe looks like this instead. So if this is the x-axis and this is the probability density axis, is the vertical axis, then, for example, if I had a probability density that said something like this, then I might say that the expectation value for where I might find the particle at a particular time is this value, and the uncertainty in finding that particle, or the uncertainty in where you think the particle is, might be something like this wide, right? So this is where Heisenberg's uncertainty principle is happening, actually. It's sort of at the level of thinking about probability distributions. If I have a moving particle, then this might be the early time picture, and the later time picture can look a little different. And if this is a rightward moving particle, maybe it's over here. But what's interesting is sometimes so as time goes into the future, this is not always true, but can be generic, can be something that happens. Your expectation value for x might move down the axis at later times, but you might find that your spread in X, that is your uncertainty in the location, might increase in time, right? So that means that your uncertainty in X might be itself time dependent. And the expectation value of X can be time dependent, right? And so, yeah, Heisenberg's uncertainty principle is all these things. Delta X and delta P are statistical issues. Based upon knowing that psi is related to the square root of probability. Yeah, so more in the next video.